Okay, let's look at viscosity and turbulence. Actually, we're going to focus mostly on viscosity and talk about how that affects the movement of fluid. So that's really the focus here. So when we're looking at fluid flow, we talked about viscosity earlier as being the internal friction. With the exception of liquid helium, which is a superfluid, all fluids have some viscosity. Now, the viscosity of air is fairly small, so in many circumstances, it can be neglected. Um, Obviously, the viscosity of water is a bit more, but if you want to go to the most extreme examples of viscosity, we can go to things like molasses. We can go to things like lubricating oil. Here, they've just colored the water so it's easier to see. You can see how easily the water flows from this beaker. Again, they just added blue coloring to demonstrate this. But in the other beaker, there looks to be like motor oil, which has a higher viscosity. And the reason why it has a higher viscosity is because as the molecules try to move past one another, the intermolecular forces provide resistance. And for these very long polymer molecules, which are used in these lubricating oils, we know this is the London dispersion force. And the longer these molecules become, the more viscous, the higher the viscosity becomes of this fluid. So when an object passes through any fluid and the fluid has viscosity, we're forcing the molecules of the fluid to actually move. And friction acts against any type of movement. So any type of object moving through a viscous fluid, a viscous medium, is going to experience drag, okay? And this resistive force for a spherical object, it's different for every shape, but for a spherical object, at a low enough velocity, follows what's called Stokes' law. And this says that the force of drag is equal to 6 pi times eta. That's that little Greek symbol that looks like an N right there, times the radius of the sphere, times the velocity of the sphere. So this viscous drag will slow, in this case, a spherical object down, because again, friction always does work against motion. If we look at when this, according to Stokes' law, when this velocity becomes equal to when the force becomes equal to the force of gravity, we're basically balancing the resistive force versus the weight of the object. And also, we have to take into account the buoyancy. We can rewrite the equation to solve for what we call terminal velocity. And this is the fastest that the spherical object is going to be able to travel through this viscous medium. So the equation looks something like this. Notice that the terminal velocity is, first of all, proportional to the radius. So as the radius becomes larger and larger of an object falling through it, obviously the terminal velocity is going to be higher and higher. What this means for most particles, which are settling out in a fluid, is the bigger particles are going to settle out first because they're going to have a higher terminal velocity. And the smaller particles are going to settle out last because their smaller radius means that they have a lower terminal velocity. The equation also depends on the viscosity of the liquid. And because there's a buoyant force involved, the density of the objects minus the density of the fluid. So again, this will explain why when we look at a stream, you know, you'll have some parts where you have very fine silty material that'll settle in certain parts where it is calmer. And at higher velocities, you're actually able to pull larger stones with you. Okay, it's pretty complex because we look at the pebbles in terms of the water moving, where their velocity would be relative to the movement of the water. So it gets a little tricky figuring that out. So terminal velocity in general, Stokes' law does not work well for objects that are not spherical. As we change the shape of the object, obviously that's going to affect the drag. Assume that the resistive force is a magnitude given by Fr is equal to K. V, K is the coefficient of drag. Well, it's related to the coefficient of drag. It's determined experimentally. We can write our terminal velocity to look like this equation right here. Okay, but again, the important thing here is to notice that the terminal velocity increases with the mass of the objects. And again, basic common sense, bigger objects are going to settle out faster than smaller objects. Okay. And again, first of all, the density of the objects that are settling have to be greater than the density of the fluid. And for rocks and water, most minerals have a specific gravity of 3 or higher. Okay. Sedimentation rate, the speed at which material falls through a fluid, is called the sedimentation rate. It's important in clinical analysis. The rate can be increased by also increasing the effective value of G. Let's go back to this equation right here. See how this right here, this G, is related to the terminal velocity? Okay. This equation assumes that there's no thermal involvement that is going to prevent particles from settling out. So let's say we have some cylinder. We want the sediment or precipitate to settle out. Okay. Without any thermal agitation, these particles are just going to go downward. But as it gets smaller and smaller, they begin to approach the size of the molecules in the liquid. The thermal motion is going to agitate them and prevent them from settling. Okay? So there comes a point where if we have sediment that's so small, it gets even worse if they're charged. That's a totally different process where their charges will keep them from sticking together. But as the particles get smaller and smaller, there becomes a point where the terminal velocity will be pretty close to 0. They're not going to settle out. So what we can do is we can enhance the effective gravitational pull. Okay, you can change G by putting it in a centrifuge where we actually create artificial gravity. So here's the idea here. When we have particles that are suspended in some fluid, okay, maybe they're blood cells suspended in plasma, maybe it's a precipitate which is suspended within some aqueous solution. Okay, if we can't just sit down on the shelf and get to settle out naturally, we need to increase G, and basically we create kind of like artificial gravity. If we think about it, the force to keep this test tube going around in a circle, okay, the centripetal force is equal to mass times the velocity, the tangential velocity, divided by the radius. Or if you want to write it in terms of angular velocity, we can also write this as m omega r omega squared, okay? So here, the effective G in a centrifuge is simply just r omega squared. Now, here's the interesting thing for this. Again, thermal agitation is going to prevent the smallest particles from settling out. Even cells in the blood are subject to this. So what we can do is we can crank G way up to overcome these thermal influences, and we can, at a high enough speed, get the densest aspects of the blood to settle out first, and then progressively lighter amounts. And again, this is what they will do. For instance, let's say we're trying to extract platelets from the blood. I believe the platelets are the densest cells. It's been a while since I've had biology. But if you want the platelets, you simply centrifuge this down, take your test tube, okay? Take your test tube and simply pipette out the densest parts of this. And again, you'll have, I believe the platelets on the bottom, I don't know, red blood cells and white blood cells in layers above that, and then the plasma in the very top layer, since it's the least dense. So the particle's terminal velocity will become this. We simply just replace G by the centripetal acceleration term. And again, the particles with greatest mass will have the greatest terminal velocity. They will settle out first. Finer particles with less mass will settle out later on. Okay, so that's sedimentation. Well, physics is sedimentation. We don't really do much with that in this course, but certainly if you've taken biology, chemistry, or especially geology, sedimentation rates are very, very important. In biology, for separating different cells, in chemistry for separating precipitates, and obviously in geology for settling different sediments. Once again, there's only one fluid that lacks any type of viscosity, and that's a superfluid. That's liquid helium. And when a superfluid flows through anything, there's no resistance to flow. So if we put liquid helium through a pipe, all the fluid would be flowing at the same velocity, regardless of where it was in the tube. Okay? Constant velocity. There'd be no difference in velocity. The problem is, viscosity means that these molecules are going to interact with the sides of a tube. Okay? So those close to the sides of the tube are going to experience the greatest drag because the tube isn't moving, and those furthest are going to experience the least amount of shear. So when we look at the cohesive and adhesive forces in a fluid, the fluid is going to be at rest when it's completely in contact with the wall, okay? That adhesive force is going to be preventing it from flowing. As we get further from the wall, the cohesive forces are going to drag the faster moving fluid to slow it down. So what results is a profile that looks something like this, okay? We can actually measure viscosity using something like this, where we have one surface which is kept at rest, one surface which is moving with some velocity v. They're separated by a distance d. And again, the fluid profile will go according to what is happening with the fluid in contact with the wall. The fluid up here is going to move with this moving wall up there. The fluid down here is not going to be moving. So if we measure the force necessary to keep this wall moving, we multiply it times the viscosity. We multiply it by the area of the two walls, the velocity which is moving, and the distance of separation. We can get a measurement for viscosity. Okay? The more viscosity we have, the more force it's going to take to move this top wall right here. So that's basically how we're able to measure viscosity of a fluid. In terms of the profile, going through a circular tube, we have, I can never pronounce this properly, Pasolini's law. I'm hoping I'm close. But Pasolini's law gives us the rate of flow through any circular tube. Again, the fluid right up against the wall is not going to be moving. And as we get further and further away from it, the fluid at the center of the tube is going to have the highest rate. So the rate of flow, how much volume of fluid we get per unit time, is going to square up by, is going to, I should say, be proportional to the radius of the pipe to the fourth power. Okay, so you can see here, obviously, if it were a superfluid, we would expect, since the cross-sectional area goes by pi r squared, we would imagine that the amount of volume that flows per time should be proportional to r squared. Okay, but actually it becomes proportional to r to the fourth, because as we can move further and further from the wall, you get more and more velocity at the center of the tube. And again, it's going to go by the power to the fourth power. Okay? So how much flow we can get through a tube will depend on the viscosity of the fluid. Water flows better than molasses. It will depend on the size of the tube, going by a function of r to the fourth power. And certainly the difference of pressure from one end of the hose to another end of the hose is going to affect how much water we can get through a tube, a pipe, or a hose. Okay? This is interesting because it doesn't take very much increase in the pipe size to dramatically increase the amount of fluid flow. Just to give you an example, in a typical home, you'll have copper pipe. Some of the copper pipe will be 1/2 inch. And in my home, I actually had a real water flow problem. So I replaced a lot of the 1/2 inch and the 3/4 inch with 1 inch piping. Okay. Now, 1 inch compared to 1/2 inch. All right. You think, well, 1 inch has 4 times the cross-sectional area. You'll get 4 times the flow. No, no. Look at this, R4. If we take 2 and raise it to the fourth power, 2 times 2 is 4, 4 times 2 is 8, so 2 to the third is 8. You get 16 times as much water through a 1 inch pipe than you get through a 1/2 inch pipe. Okay? Even through a 3/4 inch pipe, just upgrading to 3/4 of an inch, you're taking 1.5 times more and raising that to the fourth power. Let's see if I can show me the calculator. Oh, it's not going to share the calculator. Oh, that's unfortunate. But if I take 1.5 and I raise it to the fourth power, just increasing the diameter by 50% increases the flow rate by 5 times. Okay, so I do a lot of my own plumbing. If you do your own plumbing, it's very important to understand that the pipe size is very critical to the flow rate. You cut your pipe diameter in half. You're not just decreasing the flow rate by 1/2 or 1/4. you're decreasing it by 16 times. Okay? Don't let your plumber cheap out on you. Okay, Reynolds number. At a sufficiently high velocity, a fluid flow can change from streamline, okay, to turbulent. And the onset of turbulence can be found by calculating the Reynolds number. Now, the Reynolds number is related to the density of the fluid. So it's not letting me write anymore. It doesn't like me. Why is it doing that? Let me kill this. Well, I lost my connection. I don't know why. Okay, let me try this again. Reset my pen. There we go. It's related to the density of the fluid, the velocity of the fluid, the diameter of the obstruction, and the viscosity. So a Reynolds number of 2,000 or below, generally we see streamline behavior, okay? As the velocity increases, okay, Reynolds number between 2,000 and 3,000 is going to be somewhat unstable, and turbulence will be around 3,000 there. Okay. All right. Surface tension. Surface tension. Surface tension is a very interesting effect that causes fluids to want to have the least amount of surface possible. And the way we can understand surface tension is this. When a molecule is sitting in the middle of a fluid, it doesn't experience any net force. All of its neighbors are pulling on it equally. But on the surface, that's not the case. On the surface, there's nothing above it to pull on it. So basically, the net force is going to try to pull the molecules to the center of the fluid. So every time a molecule comes to the surface, it gets pulled inward. All right? Now, what this means is the net effect is to reduce the surface of a fluid as much as possible, and the geometrical shape with the least amount of surface for the same amount of volume is a sphere. So all the molecules are going to try to pull themselves into a ball due to their cohesive, their stickness together forces, their intermolecular forces, causing this to ball up. Now, we know that water has very strong cohesive forces. It has a hydrogen bond. So water tends to have a very large surface tension given its other properties. All right. And we can see that here. We can see this little bead of water pulling itself into a ball due to this surface tension. And again, the stronger the cohesive force, the more surface tension, the more likely it is to ball up. Okay. You don't see this as much in non-polar molecules. They don't have as much surface tension because really the cohesive force is more of a London dispersion force. Hydrogen bonds create a very large surface tension. Metallic bonds in mercury create a very large surface tension. So the stronger the intermolecular, the interatomic forces, the more surface tension you tend to get. And surface tension actually allows us to float a steel needle on the surface of water. And here's the weird thing. It's actually hard to derive this, but has to do with the profile when we're looking at this. Water wants to keep as little surface area as possible. And because the needle is very, very long, we can generate a fairly large surface tension and keep it from sinking. Now, the force of surface tension is going to pull in these two directions, and as long as it exceeds the weight of the object, it's not going to sink. A needle has a lot of surface area for very little volume. But we know as we scale anything up, the surface area generally goes by the square of its dimensions, whereas the volume, which is related to the mass, goes by the cube. So volume gets bigger faster than area. Only very small objects can use surface tension to prevent them from sinking. And here's the surface tension units. It is a number of newtons that we get for the length of the object on the surface of the water. We can calculate it, or I should say we can measure it using a device like this. See how much force it takes to pull the wire ring off a film of water. We can use certain chemicals called surfactants to break surface tension. Surfactants generally have a non-polar end and a polar end. And what this reduces is the amount of surface tension by essentially canceling out the cohesive force. Again, the surfactants will sit on top of a polar solvent like water, and you'll have this non-polar end at the top, the polar end interior to this. And again, this reduces surface tension. That's why we use detergent, which is a surfactant, to break things like the surface tension, which would allow us to wash off dirt or other fatty things. Oops. So closer look at surface of liquids. Cohesion is the process where a liquid will stick to itself. Adhesion is a process where water sticks to other things. This leads to what we call a meniscus. Now, if water likes to stick to something more than it likes to stick to itself, we get this positive meniscus. You can see it curves upward because it wants to maximize the surface area with the glass. Okay? So water has a strong cohesive force, but there's a stronger adhesive force to the glass, producing this concave meniscus. Mercury, being a metallic bond, has an even stronger cohesive force. So although it likes to stick to the glass, it likes to pull itself to minimize the surface area even more, creating this convex meniscus. So you can always, get an idea of cohesive and adhesive forces for liquids by seeing what type of meniscus they create. I'm going to skip some of this. Capillary action is also a result of the cohesive and adhesive forces, but it's actually the two working together. Okay. Here's how capillary attraction works, or action works. Okay. First of all, cohesion wants to keep this surface area as small as possible. The adhesion wants to keep this surface area as large as possible. So both the adhesive force of the water to the glass walls and the cohesive force, which is creating the surface tension, is going to cause water to go up a small capillary, creating this capillary action. Okay? Now, the smaller the radius of this, okay, and again, as we get smaller and smaller, we're reducing the volume and therefore the mass faster than we're reducing the surface area. So the ratio of surface area to volume gets larger as we go to a smaller and smaller radius capillary. So smaller capillaries are going to pull up a liquid much easier. If the cohesive forces are greater than the adhesive forces, we get this negative capillary attraction, okay? This would be the case of, for instance, mercury. We have this negative capillary action. And again, here we can see gravity wants to pull the column of liquid downward. Capillary action wants to pull it upward. Capillary action is dependent on the area. Weight is dependent on the volume. As we go smaller and smaller, area becomes larger in ratio to the volume. Lastly, transport phenomena, the movement of fluid may be due to different concentrations, as opposed to movement due to a pressure difference. Concentration is the number of molecules per unit volume. So fluids will tend to flow from an area of high concentration to low concentration. This, again, is really a result of the thermal motion, okay? Molecules are bouncing all over the place, all right? The thermal motion wants to have an equal number of molecules of one type on one side and equal amount on the other type, because there's an equal probability of crossing one way to the other when the concentrations have equalized. Okay. So molecules will move from a higher concentration to a lower concentration by what we call Fick's law, okay? This is the amount of mass that passes per unit time, okay? It depends on the difference in concentration between two bodies of liquid. L is the thickness of the membrane, okay? A is the surface area, and D is the diffusion coefficient, which depends on the molecule through the material. So again, molecules want to go from higher concentration to lower concentration because it's just statistically favorable. If you have more molecules of one type on one side than the other, okay, you will have a higher probability of going from left to right than from right to left, okay? Twice as many molecules, twice as great is the probability. This can lead to some interesting effects. If I have a semi-permeable membrane that only allows the liquid and not other dissolved things like ions through the semi-permeable membrane, you will actually get the liquid migrating this way, okay? Because again, the concentration of solvent molecules is greater on the left side than the right side, and it will move to the right to try to balance the concentration. This is opposed by another force, which of course is gravity. Gravity wants to send the fluid in the opposite direction. So you'll reach this equilibrium between the height of the solvent and the concentration. The concentration won't completely balance out, and the height won't balance either. So osmosis is the movement of water from a region where the concentration is high across a selectively permeable membrane into a region where the concentration is lower. In this case, it might be salt concentration, electrolyte concentration. We actually can use a process called reverse osmosis to purify water, okay? Let's say we have salt water on this side, and we push the water through the semi-permeable membrane. Well, salt can't go through the membrane. So what that'll do is, in what we call reverse osmosis, create pure water on one side of the barrier and leave all the contaminants on the other side of the barrier. And this is, again, what's sometimes called reverse osmosis. So you hear the term reverse osmosis filter. They're just pushing fluid through a semi-permeable membrane using pressure. This is good for decontaminating contaminated water. It's also very good for desalinization.